All right, welcome everybody. We're here to take a look at class, this video being made in lieu of class for the Monday, Wednesday, Friday algebra meeting at 8 o'clock. This is Friday, October 4th. A fairly short lesson, so there's time to look at some practice problems, some warm-up review type problems, and get a little bit more practice working on the problems that we're likely to see in the future in terms of homework problems, test questions, those kinds of things, and also to preview what it is we want to talk about in this pretty short lesson here, lesson number 13, to finish up these linear functions. All right, something that we talked about in the previous lesson, in lesson 12, when we introduced the idea of a linear function and started talking about these equations of lines. One very, very common problem we run into is this first example here. Find the slope of the line passing through 2 points. All right, so obviously this requires us to understand how do you calculate the slope? What's the formula for calculating the slope of a line? So here it is. All right, so change in the y's, y2 minus y1, divided by the change in the x's, x2 minus x1. For these two specific points, we just simply supply the formula, the coordinates. So we'll have -5 minus 1, that's the rise, divided by 2 minus -3, which is the run. And being careful with the signs and simplifying here, we get -6. So we've actually fallen when moving from this first point to the second point, 6 units. And then the run from this first point to the second point, 5 units. So there's the slope of this line. In the second question, what we did is after we get a pretty good feeling for what is the slope of a line, how do you calculate it, and what is the meaning of that slope of a line, then we're interested in writing the equation that describes all the points on a particular line. And there's several different situations we find ourselves in, this one here being fairly common. Write the equation of a line that passes through a specific point, so we have 1 point, and we have the slope already been given to us. So this is a increasing line because the slope is positive, and we're increasing it at a rate of rise 3 units for every 4 units of run. This is a perfect candidate for the point slope form, and so we can fill in y minus y1 equals to m slope times x minus x1. And we have all of the values to fill into this form of writing the equation of a line. So we just simply put our values in, right? So here's pertaining to this specific line we're talking about. Y minus 7 is equal to 3/4 x minus -4, which is really x plus 4. Right? And we can just leave it that way. If we're asked to write it in a different form, if we're asked, for example, to write this line so that it can be graphed easily, in order to do that, we would want to solve for y, which is putting this into slope-intercept form. That's not terribly difficult to do. Right? So we have the equation of a line already. Let's just go ahead and move the 7 over. We'll distribute the slope. So you got y equals to 3/4 of x. 3/4 times 4 is 3. And then we're going to move the 7 over. So we're going to have that plus 7 over there. So it's very likely if we're asked for this format, we would see the equation of a line written as y equals to 3/4 of x plus the 3 and the 7 give me 10. Right? All right, let me box that guy up. In the third problem, it's a graphing question. So we have the equation of the line given to us. The idea here is how do we utilize what we know about this equation of a line and the different formats for writing the equation of a line? How do we use it in order to easily, quickly graph this line? Now notice the equation that we're given here, it's not in this point slope-intercept formula, nor is it in the point slope form. This is in the general form. General form, actually, it makes it pretty easy when it comes to just graphing because we can easily, quickly identify with very little work the two intercepts, the x-intercept and the y-intercept, if they exist. Very easy to find, right? Remember, the idea behind finding a y-intercept is put a 0 in for x, and so if we do that, we'll have essentially covered up this term, right? 2 times 0 would be 0. And then you're just trying to figure out, well, what is the y value? So you can get the y-intercept really easily. The y-intercept happens up at 2, right? So you got 0, 2, there's your y-intercept. And to find the second point, which we know we only need a second point to graph this line, we can find the x-intercept quickly. That means plug in a 0 for y, which amounts to covering up this term, and then just solve for x. So we can see when you divide by 2 on both sides, x has to be 3. So 0, 3, 0, there's my x-intercept. 2 points is enough to graph the line, and so we just draw a line through those 2 points. All right, in the fourth warm-up problem here, and I think that there are actually 5 of them total, the fourth one, which of the following equations describes a line with a slope of 0? All right, so here's what we know about these kinds of lines. If your line has a slope of 0, it must be a horizontal line. Right, this is a constant function that we're talking about. And all horizontal lines, they always have the equation format y equals to some number. And I'll use little b to represent that some number, whatever b happens to be. So notice there's 0 x's in this equation. So as you go through your choices, you can obviously cross out the first one. You got x's in the second one, 2x plus y equals 0. That's going to be one of these slanted lines, so that's no good. C is very promising because there's no x's in there. You can quickly cross off D because you got 2 x's sitting in here, so get rid of that. Yeah, it looks like C is the one. And you can write it in this format where we've got isolated y value. Just divide through by 3. You can see that y equals to -7 over 3. Right, so this is a horizontal line down at a height of -7/3. So that's the only one of the 4 equations that were given. They're all going to graph into lines, but that's the only one that has a line with slope of 0. All right, the final question before we get into the lesson for the day, a little reminder and kind of a combination question here of parent functions and transformations to those parent functions. Identify the parent function and the sequence of transformations to obtain the graph of this function I've labeled as g. And you notice it's -3 times x minus 2 squared plus 7. All right, the parent function here is that squaring. F of x equals to x squared. That's my parent. We know that that's your basic parabola with the little bottom, the vertex, sitting at the origin. We're going to take this parent function and we're going to send it through the transformations required to generate this function that we've called g of x that we're dealing with. All right, so the first thing that happens to x as it comes in is we're replacing x with x minus 2. We know that that's a shift. It's a horizontal shift. And that horizontal shift is to the right, exactly 2 units. That takes care of the -2 right in there. The second part of the transformation is we're multiplying by 3 times the quantity we're squaring, and so we know that that's a stretch. It's a vertical stretch. So you got a vertical stretch by a factor of 3. That takes care of that little multiplying by 3. We're also multiplying by a negative out here, and we know multiplying a function, the entire function, by this negative, it's going to flip it upside down. It's going to be what we refer to typically as a reflection about the x-axis. So now the parabola that used to be opening up like this, now it's been flipped over and it's opening down. So check. The last thing to take care of is, what about this +7 tacked onto the end? So that's the fourth transformation in this sequence. We know that that's a vertical shift and it's up. So we got a vertical shift, up 7 units. Check. So we take the parent function, and we send it through this sequence in this order of these transformations, we can easily produce the graph of g of x. And we were just asked to identify the sequence of transformations, not to supply the graph. So we're sufficient. We're good to go. All right, so a little 10-minute warm-up, some good practice problems in here. I would anticipate you'll see some of this, examples like these for practice on homework problems. Very likely one or two of these will show up on our next exam as well. All right, here's the lesson for today. Section number 13. All right, so wrap up kind of part 2. It's a very short part, but part 2 of these linear functions. In your textbook, this is chapter 4, section 1. If you want to read for some additional examples and some more practice problems. The objectives here are a short list, right? We just want to discuss pairs of lines, and some special pairs of lines, specifically how do we deal with and understand relationships between lines that are parallel or lines that are perpendicular to one another. And there's a couple of neat little features that'll help us with these special relationships between two lines. The main point of today, the key part, is this second objective. We're going to define what we call the average rate of change between 2 points on a nonlinear function, right? So we want to extend this idea of rate of change, i.e. slope, onto these functions that are not lines, that have some curvature to them. All right, let's take a look at these parallel perpendicular lines first. Two lines are parallel if they never intersect. No matter how far you extend, the two lines will not cross one another. What's important to note, if two lines are going to be parallel, so they're going to run right along next to each other, equidistant from one another, then there has to be a very, very easy relationship describing the slopes of those two lines. The slopes of parallel lines are equal to one another. Right? The y-intercepts have to be different, but the slopes, they're going to be the same number, same rise over run ratio for the two lines. All right, some notation. We write line 1, right, so L1 is parallel, and that's what those two little vertical bars represents, is the phrase parallel, to line 2. And what that tells you is we know the two slopes are the same. M1, right, so slope coming from the first line, is equal to M2, the slope for the second line. All right, for perpendicular lines, two lines are perpendicular to one another, means that they intersect at a right angle. At a 90-degree angle, right? That's what we call a right angle. What's true about the slopes of those two lines with a perpendicular relationship is that the two slopes are negative reciprocals of one another. And we'll look at a couple of examples. Well, what do you mean by exactly a negative reciprocal? Notation-wise, here's how we indicate that two lines are perpendicular. We write line 1, so L1 is perpendicular, so that's what this looks like, an upside down capital T, to L2, and this happens when M1, the slope of the first line, times the slope of the second line is negative 1. Right, so here's the definition of what we mean by two numbers being negative reciprocals. When you multiply them, you get negative 1. So just as a quick example, if the slope of the first line, let's say it's 3 over 4, if M1 is 3 over 4, and we know line 1 is perpendicular to line 2, then the slope of the second line is the reciprocal, so 4/3, negative. And when you multiply those two slopes, sure enough, you're going to get exactly negative 1. All right, a couple of examples here utilizing this new information we have about parallel lines and perpendicular lines. Write the equation of a line that's parallel to this line, right? So we have a line that we already probably have graphed. We're trying to generate another line that runs right next to this one that's parallel to it, and it has to pass through the point 2, -12. We're going to use point slope form. We also want to write it in slope intercept form. So we want both formats for this problem. They're probably two separate little fields we have to fill in. All right, so here's what we know about our line. The line we're trying to write the equation for, call it our line, has a slope same as this one, -5. Use the point, and we have this point 2, -12 with that slope, y minus y1, which is y minus 12, -12, so it's really y plus 12 over there, equals to the slope, -5, times x minus x1, which is 2. So there's the first format, the point slope format. We'd leave it just like that. And then if we want the slope intercept format, that just means solve it for y. So we can identify the slope and the y-intercept. So it just means that we have to take this guy and transform it a little bit. Y plus 12 is -5x plus 10. Subtract the 12 from both sides. So y is equal to -5x minus 2. And that's same line. It's the slope-intercept form. The slope and the intercept are easy to identify now. All right, in the second example, and I think we'll utilize what we know about slopes of perpendicular lines here, the equation of the line perpendicular to, so again, we have a line that has been described for us. We're trying to generate the equation of a line that's perpendicular to this line, so a whole separate line. This line right here, we have to figure out what the slope is. That's pretty easy to do. It just means, solve for y so we can see what's the slope. So you would have, y equals to, you're going to move the x over, move the 13 over, and you're going to divide by 3. So x is -1/3, y is -1/3 of x plus 13 over 3. So we know the slope here for this line is -1/3. We can tell what the slope of our line is going to be based on knowing the line, the slope of the perpendicular line. So here's our slope. Our line has slope, negative reciprocal of this, which is going to be positive 3/1. We have a point, 7, 2. Use it. So we use the point, and we generate the equation of this line. Y minus 2, y minus y1 is equal to the slope times x minus x1. And that's it. We weren't asked to, we're asked to write this in standard form. Okay, so we're going to get all the x's and the y's on one side, the constant over on the other side. That's no problem. So you got y minus 2 equals 3x minus 21. Move the 3x's to the left. So we'll have -3x's plus y. We might as well add the 2 over so it shows up over on the right. And that's going to be -19. Right? So there's the standard form of the equation of this line that we just built, which is what we were asked for. We were asked for the equation of the line and put it in this format. All right. So perpendicular, parallel lines, pretty neat little relationships. We can use that information when necessary. All right, here's part 2. Here's what I would consider to be the more important part here. This idea of average rate of change. And this is a huge idea, particularly for any individuals that want to move on and study some form of calculus, maybe necessary for your degree plan. This idea of average rate of change is the basis for starting that discussion. What we mean by the average rate of change, and I'll abbreviate this as ARC for average rate of change. The average rate of change measures the change over an interval, right? An interval of the domain, so x's, for any function, not just lines. Lines have a constant rate of change. So we don't have to discuss this average rate of change. The rate of change for a linear function is always the same. But for curves that move up and down, maybe the parabolas or square root functions or whatever function has some curvature to it, when you look at the graph, the average rate of change is simply looking at extending this idea of slope. It's the slope of the line containing these 2 points. So x1, f of x1, that's your x1, y1 really, and x2, f of x2, which really is x2, y2. Here's the formula. So the average rate of change in the function, we'll call the function f, as x changes from x1 to x2. So on the interval, this interval that we're talking about, this is the interval from x1 to x2. The calculation, this is equal to the rise over the run. F of x2 minus f of x1, right, which is really y2 minus y1, divided by x2 minus x1. So there's your rise over your run. Your numerator here is your rise, and here's your run. Now, the line that contains these 2 points, x1, f of x1, and x2, f of x2, those 2 points are on the curve. The line that connects them is called the secant line to the curve. And so depending on the 2 points you pick that are on the curve, you're going to generate the slope of a different secant line. All right, here's an example of making this calculation. I'll suggest some steps on how to make sure you get everything into the right position for making this slope calculation. Find the average rate of change, f of x, and notice it's a cube function, 3x cubed minus 1. So it's definitely curved. This is actually the basic cube function that's been vertically stretched by a factor of 3 and then shifted down 1 unit. So we have an idea of what it looks like. It's this s, this kind of snake function. We're interested in the interval -3 to 3 for the x's. So those are your values right there. x1, the starting point, is -3, and x2 for the run, the ending point, is +3. So we have an interval of 6 units of the domain that we're interested in. You plug those values in to get the y coordinates at those 2 locations. So f of x1, that's just f of -3, which you just plug in -3 into this function. So that's 3 times -3 cubed minus 1. And you can evaluate that number on your calculator if you want, or you can just do it in your head. Right? 3 cubed, this is going to be -27. Times 3 is -81. All right. And then, is that right? Yeah. 27, 81, -82. And then for the f of x2, plug in the 3. So we'll have 3 times 3 cubed minus 1. And again, 3, put my cube on there. Cube. 3 cubed is 27. Times 3 is 81, minus the 1 is 80. All right, so we have our 2 points. The average rate of change, we can now calculate. It's 80, right, check, minus -82, and then 3 minus -3. x2 minus x1. Calculate. We got what over here? 162 over 6. And when you reduce, this turns out to be 27. So on average, this function changes at a rate of 27 to 1 over the interval when x starts at -3 and ends at +3. Right? So notice it's nothing more than a slope calculation, a slope of a line where we've picked 2 points on the curve and generated the slope passing through those 2 points. All right, here's a second example, example 4 of this average rate of change. This time, rather than having access to the equation for the function, we've been given the graph, which in a lot of ways, in a lot of instances, it's much simpler to work with the graph. We can just grab the information off, and I think particularly in this case, we can visualize exactly what's happening with this average rate of change notion. All right, the graph illustrates the decay of a radioactive substance over T days. So the independent variable here is time measured in days, and then the y-axis, the amount we're measuring here in milligrams, this is this radioactive substance. The question or the instruction for us is to estimate the average decay rate, so the average rate of change, as time changes from 5 days to 15 days. All right, so at 5 days, so this is my x1 value. At 5 days, you go up, we're sitting right there. It looks like we have an amount of that radioactive substance, 12 milligrams. So we've got this point, 5 days, 12 milligrams. At 15 days, so we span this interval right here from 5 over to 15. At 15 days, it looks like we're sitting right at 6 for the amount of that substance. So 15 days corresponds to 6 milligrams of the substance. So there's your 2 points, right? There's your x1, f of x1, x2, f of x2. We want to calculate what's the average rate of change over this interval, and so we're building this line, and it's the line that connects these 2 points. This line right there. And so we want the slope of that line. The average rate of change in the amount over the interval of time, 5 days to 15 days. We can calculate this. This is equal to 6 minus 12, right? So y2 minus y1 over 15 minus 5. And so you got negative 6 over 10, which reduces down to negative 3/5. All right, so this idea of calculating the average rate of change for a nonlinear function, we have to know what interval of interest for the domain, what's the x1 and the x2, 15 was the x2 here, and then we're allowed to calculate this pretty easily. We just have to figure out what are the 2 y values for those 2 x's, for the endpoints of my interval of interest, and then just generate the slope. If I pick 2 different endpoints, like say I'm interested in going from 0 to 10, right, we would have a different calculation for the rate of change because the interval is different that we're interested in examining. All right, so I hope that this lesson wraps up these linear functions well for you. Obviously, don't forget to take a look at the homework assignment on WebAssign that's associated with this section 13. And then next week, we'll start talking about this upcoming exam. We'll also start looking at a couple of additional things about functions that we want to throw in and kind of wrap this little block of material up. All right, hope you have a good weekend.